Okay. So now we're talking. So we talked about acids, acids and bases, and equilibria for acids and bases. So now we're going to talk about equilibria of other. Okay. So Evelyn and Elise. Okay. So we're now going to talk about equilibria of other types of reactions, precipitation reactions, um, um, metal halide reactions. Okay, so we have equilibria of, I'll just put other classes. So equilibria of other, or I should say reaction classes actually, of other reaction classes. So the other type, instead of acids and bases, is that we can talk about precipitation and dissolution. So precipitation and dissolution. So if we have a solid, we'll say copper 1 chloride. So copper 1 chloride, um, when we ionize it, well, we can get copper plus. We get some aqueous ions from that, and then we'll get some chloride ions as well. And while we're going this direction, so if we go from solid to these ions, this is what we consider dissolution, right? If we're going in this direction and we're taking ions and we're making a solid, is that what we would consider precipitation? Okay, so dissolution, precipitation, and precipitation, if you don't already know, is when when a solid precipitates out of the solution, right? So we mix these ions together, and from that mixture of those ions is that we have some solid form. We have some solid that precipitates from that solution. So another K value, right? So we have like Ka, we have Kw, Kb, right? And we have, Ka. So here's another K value here. So we're now going to deal with what we call Ksp, right? Where Sp is what we consider the solubility product, right? Solubility product. But how we write it, it's always again, products over reactants, right? So our KSP for this particular reaction would be, and notice here, right, that this is a solid, right? When we do these, um, when we convert these formulas into these K values, is that we only deal with aqueous ions, gas molecules. So here we have a solid, right? So if I write the whole thing, products over reactants, so we're going to have the concentration of copper times the concentration of chloride over concentration of copper chloride. Well, essentially, we're just going to use the value of 1 here, is that we're really not going to consider that particular concentration. So we can actually just simply rewrite this as the KSP is equal to the concentration of copper multiplied by the concentration of chloride. And, excuse me, and that would end up being our formula here when we're looking at that. So these KSP values, these solubility product values, let's just give an example of one. I'll give you a couple here. So we'll say that copper chloride KSP is equal to 1.2 times 10 to the minus 6. And then we'll say, how about iron hydroxide? Iron 3 KSP is equal to 4 times 10 to the minus 38. Okay, when we have a small KSP, right? So a small KSP, the equilibrium lies, I'll put lies to the left, right? So here we have two reactions here. So we have copper chloride and we have iron 3. So with a small KSP, the equilibrium lies to the left, right? And we can see absolutely just how small this is. So for the smaller the KSP, the less soluble it is. Okay, the smaller the KSP, the less soluble it is. Is that here, because this is such a small KSP, the equilibrium lies to the left. I should put these in here as well. Right? Is that iron hydroxide is not very soluble, right? Not very soluble. Copper chloride, KSP's is still small, but not as small as this 4 times 10 to the minus 38, right? So here we could actually consider this to be slightly soluble, right? Uh, so the smaller the KSP, right, the equilibrium lies to the left. So let's take a look at some other ones here. How about lead hydroxide? Because we could also see this. So this is lead 2. Excuse me, this cough is getting the better of me today. So sometimes we're going to have 3 ions here. Not just 2, but we have 3 ions. And again, we'll just go ahead and separate these, right? So we would separate this into lead 2 plus some hydroxide plus some chloride, all of it being aqueous here. And if I was going to write a KSP for this, it's still products over the reactants. So my KSP, so I don't worry about the solid because that's just simply going to be 1. So we're going to have the concentration of lead times the concentration of hydroxide times the concentration of chloride. And I would have 3 concentrations here in this. So Um, what happens here is that sometimes we do get this OH here. Sometimes we see it here. And in a case like this is what we're going to go. Let me see if I should talk about this in a little bit. So we have hydrated. Let me look at my notes. As we did talk about this slightly um, in chapter 14. We talked about solvation fears. So this here we would consider this a solvated metal ion, right? Where we have what we call a solvation sphere around that. So here we would have lead 2 plus, and then that would just simply be surrounded by some water molecules. Right, so solvated metal ions, where this here, right, all these water molecules are what we consider a solvation sphere. Right, we're just going to have this sphere of water molecules surrounding it. So we have this what we call solvated metal ion, if that's a term we're probably going to need to know for the exam. So when we're talking about KSP and solubility, there's kind of a general formula for these reactions, right? We always have some type of general formula that we can make these reactions from. So our general formula is this, is that we're going to have some metal and some amount of moles to it. Then we have an anion, and then I'm going to put some different colors here. And then some amount of moles of this anion, and then we have it as solid. So this is my solid, and this solid is going to ionize, and however many moles of it, well, we now put that in front. And this may seem a little confusing, but I'll clear it up. Right? We have the metal charge. You know that's going to be a positive charge there. We're going to have that as aqueous because we're dissolving that. However many moles of my anion, and then the negative charge on that anion there. So if we had to, we could just kind of follow this general formula here. So I'm just going to put general formula. So let's try it. Let's try one. How about CR3? We'll put ASO4, and how about two of those? And this is a solid. All right. So here, I'm gonna highlight these red here, and just so we know what we're looking at here. This will be orange here. So I'm gonna match these values up here. Right? Is that because I have 3 moles of that, right? That now when we ionize this, I'm gonna put that 3 there, and then we have I'll put it in black here. Right? 3 chromium. And I can't forget the charge on chromium, so that chromium is going to be +2. And this is going to be aqueous, plus we're going to have 2 of these anions that are AS, arsenic oxide. So here we have 2 of those, and the charge on that is going to be 3 minus. Right. So that's all really this general formula is saying, is that anytime we can always split these up using this general formula. You know, however many moles that I have here is how many moles I put in front. However many moles I have here is how many moles we have out front. So with the general formula, because what we don't want to do is we don't want to do this. This is completely wrong. Please don't even copy it. But this has happened in the past, is that students are kind of unsure and they go CR3 and then they do this, plus they go ASO4, 2, 3 minus, and that is just complete garbage, right? We don't split up compounds into ions that particular way, right? So I hope you didn't copy it. Please don't. That is completely wrong, and we don't want to do it that way. Let's take a look at another one. How about one that's not, it's a little easier than that. How about we look at magnesium hydroxide, solid, right? So if I'm going to ionize this and turn these into ions, well, I have one magnesium ion. It's 2 plus, and I'm going to put that as aqueous. Plus, I have 2 hydroxide ions, 1 minus, and that it's aqueous, right? And again, they both follow that general rule that we have there for taking these compounds and splitting them up into ions. So let me give you a value here. Let me give you a value. How about um, in order to calculate the KSP, right? Because remember, the K value is at equilibrium. All these K values are at equilibrium. Okay, so if I give you the concentration, let's give you the concentration of magnesium, and let's say that it's 1.31 times 10 to the negative 4, right? So looking at this, so this is again, at equilibrium. If I know this concentration, right? Well, this concentration here, the concentration of the hydroxide is twice as much. It's twice that of the magnesium, given this final concentration here. So we can write this down. We'll say at equilibrium, the concentration of hydroxide is twice that of magnesium. Right? So in order to calculate the concentration of hydroxide, well, the concentration of hydroxide is equal to 2 times 1.31 times 10 to the minus 4. And we can calculate that concentration. That concentration, I don't need a calculator, it's just going to be 2.62 times 10 to the minus 4. And we now have the concentration there. So if we wanted to calculate the KSP, right, our KSP, let's not forget this formula here. Let's write it first. So our KSP is going to equal the concentration of our products, Mg2 plus, and our hydroxide. But notice this value here again, right? I have this 2 here, which means that I need to square that value. And I know what that value is. Oh, I know what both of these values are sitting here. So here's this concentration. Here's this concentration here. Is that we can now write this as the KSP is equal to 1.31 times 10 to the minus 4 times 2.62 times 10 to the minus 4 squared. All right. Can somebody calculate that and give me the mic? Yeah, someone go ahead and calculate that for me. 9.00, so we have 9.00 times 10 to the minus 12. And that is our solubility product, right? KSP is our solubility product. Now, as far as these values go here, as far as these values go in here, this is what we're going to consider molar solubility, right? Molar solubility. So molar solubility are the moles of solute. Moles of, you know what? Better. How about moles of, yeah, moles of dissolved. Moles of, because these are ions here, moles of dissolved solute per, my headset went off, moles of dissolved solute per liter of saturated solution, right? Moles of dissolved solute. So moles of dissolved solute, right? And it's still a concentration, right? A molar solubility is, moles over liters, right? This is molarity. And when we talk about molarity, we're talking about aqueous solution, something that's liquid. I'm taking this solution and mix it with this solution. We get some concentration here. We talk about anions. These anions, these cations, come from formed solids. It would be 8.99 times 10. There's no rounding. Okay, yeah, I'm good with that. 8.99 times 10 to the minus 12. So when we talk about molar solubility, we can consider that very similar to just molarity. We have some mole, not some mole of some molecule, right? But we now have some mole of dissolved solute per liter of saturated solution. So let's see if we can calculate that now. So we can absolutely calculate the KSP. Is if I have some concentration at equilibrium of the one of the anions, one of the cations, is that we can definitely calculate the KSP from that, right? So now let's try calculating the molar solubility, right? Let's calculate the molar solubility if you're given the KSP, right? So let's determine molar solubility from KSP. So determine that from KSP. So let me give you a KSP value. KSP of silver 1 iodide is 1.5 times 10 to the minus 16. All right. Well, let's go ahead and get our reaction together. So we have silver iodide as a solid. I'm going to get some silver ions that are aqueous, plus I'm going to get some iodide ions that are aqueous. I was just seeing who was all here. Got one person missing. All right.
Will we do an ice table here or no?
Yes, we absolutely will do an ice table here.
Oh, okay.
Yeah, we will do an ice table simply because, and if we take a look at this ice table,
Mm-hmm.
the only information I have is just the KSP, right?
Yeah.
So, and the KSP, we need these values here. We need this value and this value here, right?
Mm-hmm.
And I don't have any concentration. All I have is this solid, and I'm going to form some ions out. So because it's a solid, I'm just going to draw a line through it because we don't do those concentrations. We're not going to have a concentration of a solid, right?
Yeah,
Uh,
it's like water, right?
it's like, yeah, exactly. Just treat it like water. So here, I don't have an initial concentration of silver or an initial concentration of this iodide, right? But I will, which means I'm going to have plus x and plus x. So this is 0 plus x, and this would be 0 plus x. All right. So essentially, we don't even have to write the 0 plus x there. We'll just write plus x. So here, let's see, we can go with our KSP. So let's see, our KSP is equal to I'll just rewrite it. 1.5 times 10 to the minus 6. All right, so 1.5 times 10 to the minus 6 is equal to x times x, which essentially is just x squared. So x squared is equal to 1.5 times 10 to the minus 6. And if we want to find out what x is, well, we just take the square root of that. So the square root of 1.5 times 10 to the minus 6 is this simply equal to x.
I
And that
got
is equal to
1.22 times
1
10 to
point
the negative 3.
to the negative 3.
Mm-hmm.
Oh, you know what? I'm sorry. It's 16.
Oh,
My fault. There it is. Is that 16? Yeah, 16. So this
okay,
should
then it's 1.22 times 10 to the negative 8.
be to the negative 8. There we go. So let me fix that there. Not minus 16. So we now have those concentrations, right? If x is equal to that, we know the concentration is equal to 1.22 times 10 to the minus 8. We know that the concentration of iodide is equal to 1.2 times 10 to the minus 8. How about another one? Let's do another one. I'm going to change the formula up a little bit just to get a better understanding here. Love you. Mwah. Okay. Let's see. How about lead iodide? Because this would be lead too. So this is going to be our solid. And we break that up into ions. So I got Pb2 plus aqueous plus I have some iodide. But I have two iodides this time. And this is going to be aqueous. And let me give you the KSP. So the KSP here, KSP is equal to 1.4 times 10 to the minus 8. All right, so we draw our ice table again. Don't going to worry about that. We're going to go 0 and 0. This is plus x, but here, this is plus 2x because I have two of there. So here, we're going to get plus x, and this is going to be plus 2x, or 0 plus 2x. It doesn't really, I don't normally write 0 plus if I'm doing that. But again, so now our KSP, when we do our KSP, we need to be just a little bit cautious here. So it's the concentration of lead and the concentration of iodide squared, right? So here we need to recall that we put 2 in here, but we also need to remember that we have that 2 down here when we do this. So here, our KSP, oh, what do we know? We know that it's 1.4 times 10 to the minus 8. So 1.4 times 10 to the minus 8 is equal to x times 2x squared. So let's go the long way. Not everybody has a let's go the long way, just to make sure that we can do this correctly without having to use a solver actually. So uh, essentially, so let's break this out. We've got 1.4 times 10 to the minus 8 is going to equal 2x squared. So we're going to have 4x squared times x. So we have 4x to the third. So 4x to the third, if I divide this side by 4, I have to divide this side by 4. And this gets us,
I got 3.5 times 10 to the negative 9.
as the answer for x, or
X cubed.
x cubed. So this is equal to x cubed?
Yeah, I still
Okay.
have to take this cube root.
All right, yep, and then we can go ahead and take the cube root of that. So we'll take the cube root of that. Hopefully you know how to use your calculator to do that. So we'll take the cube root of 3.5 times 10 to the minus 9, and this is going to equal x. If you don't know how to do a cube root in your calculator, you could also put this in your calculator. Um, you can put, let's see, if I'm going to take a square root, you can take a square root like this. We'll just say 4 to the 1/2. So 4 to the 1/2 is equal to the square root of 4. Right? So if we're going to take a cube root and you don't have a cube root button, you can actually do 3.5 times 10 to the minus 9 and do that to the power of 1/3. And that's the same as doing a cube root. So what is x equal to?
I got 1.52 times 10 to the negative 3.
So x is equal to 1.5 times 10 to the minus 3. Right? Right, so if we wanted to know the concentration of the iodine, it would be twice that, right? Twice this concentration. But again, we can now figure out the equilibrium concentrations by knowing the KSP. Is that we can definitely calculate these molar, well, I'll call them molar solubilities. I shouldn't say concentrations. I should say molar solubilities. It's the same thing, but I should be saying molar solubility. All right. How about calculating? This one's a little bit tougher. So just kind of moving on, adding to what we already know, adding to ice tables. Um, and I don't think we'll need an ice table for this next one here, but we are going to need to recall some stoichiometry here. So how about calculating? Oh, come on. So let's calculate KSP from gram, what we call gram solubility. And the whole reason why we're even doing this is that we're going to eventually predict some solubility, right? If I put these two, is it going to precipitate? Is it not going to precipitate, right? So this is kind of the purpose of us kind of learning these methods here, trying to understand what our KSP is, our solubility product from these ice tables, from the molar solubility, large values of KSP, small values of KSP, to eventually just look at some problems and be able to determine through some calculations whether it's going to dissolve or not dissolve. So calculate KSP from gram solubility. So gram solubility, when we take a look, we need to convert gram solubility into moles of solute per liter, right? So mole solubility is something like this. So gram solubility, if we take a look at this, so how about something, um, molybdenum, maybe some ones we've never worked with before. And we'll say that the gram solubility here is 0.00179 grams per 100 milliliter. So this is what we consider gram solubility, right? I have a certain amount of grams dissolved per 100 milliliters, and that's what we consider gram solubility. But in order to calculate KSP, we need molar solubility, not gram solubility. We need molar solubility, which means that we have to convert these grams per milliliter into moles per liter. And we just do that with a little bit of stoichiometry, using a little bit of conversion factors. Right, so essentially this here, so we can actually convert that into liters pretty easily. So 1,000 milliliters over 1 liter. And this is going to be just move the decimal, 0.179 grams per liter. All right, so we've kind of gone, around the issue of the 100 milliliters. So now we're in liters. So now we have to convert these grams into moles, right? And if you already didn't know that, yes, we have to go to the periodic table, right? So we go to the periodic table, and let's look all these values up. Do I have a periodic table? Oh, let's see. All right, there's a good periodic table. All right. So for lanthanum, let's get all these values together. So for lanthanum is, how many do I have? I have 2 times 138.905. Let's see, for molybdenum, this is going to be 3 times 95.95. And for oxygen, this is 12 times 15.999. All right, so if somebody could do that math, let me know how many grams per mole we have. All right, slow down,
I
give
got
everybody one.
I got 757.648. 648.
Grams per
Yeah.
mole. Yep. All right. So 77.648 grams per mole. We do have to convert that. What we have for currently is we have 0.0179 grams per liter, and we need moles of solute per liter. So if I multiply that by 1 mole of this stuff over the 757.648 grams, well, these units here cancel out, and I will have moles per liter, and that value,
2.36 times 10 to the negative 4.
negative 4,
4.
negative.
Yeah, negative. I got negative. Oh, wait. I know what I did wrong.
Negative 5.
Yeah, I think it's negative 5. Yeah, negative 5 because
Okay,
I forgot a
negative.
0.
Gotcha. All right. So that is our concentration. So we now have 2.36 times 10 to the minus 5 as our concentration here. Well, let's take a look at the formula and let's see if we need an ice table, because we do have that concentration here. So here, we're going to put this is our solid. We're going to break it up into 2 moles of lanthanum aqueous, and that's going to be 3 plus I'm going to have molybdenum oxide. This is going to be 2 minus, and I have 3 of these, and these are aqueous. Okay, so by looking at this, we can do the stoichiometry here. The stoichiometry is rather simple, but I don't think it's necessary, but I will go through it real quick. So this is how, so if I know this concentration here, and again, this is just some simple stoichiometry here. Is if I know that concentration, let's see, so I have 2.36 times 10 to the minus 5 moles. Put moles per, I'll just use the big M here. Their concentration here. Moles per liter. This is per liter of solution. I'm just going to use moles. So 2.3 times 2.236 times 10 to the minus 5 moles of let's see. An unnecessary step, but I think we should probably go through it anyways. And then if we do some stoichiometry, for every 1 mole of this, I have 2 moles of this, right? So these units cancel out here, these units cancel out here, and essentially what I have, so if I want to know the concentration of this, it's equal to, what is that equal to? 2.36 times 10 to the minus 5, 4.72. I don't need a calculator for that, so that's equal to 4.72 times 10 to the minus 5 of, right? So essentially it is just 2 here, 2 times 2.36 times 10 to the minus 5 is equal to 4.72 times 10 to the minus 5. Right? So we really don't need to do the stoichiometry here, but if you feel you need to, that's perfectly fine. I won't stop you. So if I wanted to know the concentration of the molybdenum oxide, well, I could do the stoichiometry again, or I could just say 3 times 2.36 times 10 to the minus 5. And now I'll need a calculator. And we got 7.08 times 10 to the minus 5. So now I have these concentrations here. And because I have these concentrations, these are the equilibrium concentrations. I don't need an ice table here. Is that all I have to do is I have to look at the formula here, and my KSP is equal to concentration of lanthanum squared times the concentration of molybdenum oxide to the third. And now let's actually put those values in here. So we got 4.72 times 10 to the minus 5 squared times 7.08 times 10 to the minus 5 to the third. And that is our KSP. So our KSP is equal to what? It's going to be a really tiny number. Don't be afraid of your calculators. Come on.
I'm so sorry. I'm so slow. I got 7.91 times 10 to the negative 22.
Yeah, an
Okay.
absolutely small number. All right, so here is our value. So let's kind of review what we did. So we've done a few things now, right? Um, is we got a feel for how to make these reactions here, taking some solid, breaking it up into ions. Is that our solubility product is this constant, right? And in order to calculate those constants, we need these equilibrium concentrations, right? So if we're given one equilibrium concentration, we can figure out what the other equilibrium concentration is just by looking at our formula, right? Just by looking at our formula here, I know that the concentration of hydroxide is twice the concentration of magnesium, right? That we've been able to make ice tables. If I'm given the KSP, well, we can take that value, make an ice table, and come up with the molar solubilities here, right? We've did that a couple times. Now we can calculate KSP from gram solubility if we're given some amount of it, some actual amount of it, and we can calculate KSP values from that. So when we're talking about KSP values, so I don't, hopefully you guys recall this. So hopefully you guys recall this Q that we have, right? So Q is equal to KSP. But this is only true at equilibrium, right? That just as a reminder, Q is our reactant quotient when not at equilibrium. Good morning. Oh, Grandma had to go to work. Close the door. Don't let the doggies out. So Q is the reaction quotient when the reaction's not at equilibrium, right? When it's at equilibrium, then Q is equal to KSP. Right? So if we have a shift when it's not at equilibrium, right? If Q is greater than the KSP value, we're going to have a shift to the left. If Q is less than KSP, we're going to have a shift to the right. Right? So if we're taking a look at our values here, and we calculate Q the same way we calculate KSP, right? Products of reactants. So when we have this shift here, if Q is greater than KSP, we're going to have a shift to the right. And a shift to the right means that when we mix this, a shift to the right means that we're going to have a precipitate. I'm sorry, a shift to the left. I'm looking at the arrow left and I said right. We have a shift to the left. We're going to make a precipitate. If we have a shift to the right, well, we're not going to have a precipitate. Is that whatever we put in there is not going to precipitate out a solid. What are you doing, sweetie? My granddaughter just comes walking in my room like it's nothing, like she owns the place. All right, so let's predict some solubility. If I give you a compound, we'll say lead phosphate. Solid. We're going to get 3 lead. This is going to be lead 2 aqueous plus 2 phosphates aqueous. And let's give you some concentrations here. So let's say the concentration of lead 2, I'll say the molar solubility of lead 2 is 0.01 molar, and the molar solubility of phosphate is 1 times 10 to the minus 13 molar. All right, well, we calculate Q the exact same way. So our calculation for Q is going to be this molar solubility, and again, here's 3, so I'm going to put 3 here. So we have to be cautious of that. I put phosphate here. Here, so I'm going to put square there. And now we can go ahead and put these values. So our value of Q is equal to 0.01 to the third times 1 times 10 to the minus 13 squared. This gives us a value of times 10 to the minus 32. 1 times 10 to the minus 32. Well, the KSP of lead phosphate is 1 times 10 to the minus 54. 1 times 10 to the minus 54. So here, our Q is greater than KSP. And because our Q is greater than KSP, we're going to have a shift in this reaction to the left. And that means if we shift this reaction to the left, that we will have a precipitate. We will have a precipitate from this calculations here. So let's take a look at some other ones. Let's take a look at some other ones we're looking at when we mix solutions, because sometimes we do have to mix solutions. So when we're mixing solutions, let's pose a problem here. So will potassium precipitate if 20 milliliters of 0.05 molar potassium ions is added to 80 milliliters of oh, I need a concentration here. 0.5 is 0.05. And let's give you a KSP value. So KSP is equal to 1.05 times 10 to the minus 2 is our KSP value. All right. Well, we need some concentrations. In order to figure this out, we need molar solubility concentrations, right? Molar solubility concentrations. And that is in the terms of moles of solute per liter, right? But we have these volumes here, right? What do we do with these volumes? Well, this kind of poses an interesting question here. So what we're doing here is that here I have initial concentration. You're taking a turn? Okay, that's fine. All right, we'll see you guys later. Okay, be careful. Initial concentration, and look what we have here. This is initial volume. Interesting. Here I have another volume, And here I have another concentration. So when we're looking at, and let me back up a little bit. I don't want to get deterred by this real quick. If I have an initial volume and an initial concentration, if I add both of these together, if I take 80 milliliters, right? Because what I'm essentially doing is I'm taking 20 milliliters of this solution and I'm mixing it with 80 milliliters of this solution, which gives me a total volume of 100 milliliters. Initial volume, initial concentration, final volume. Anybody take a guess what we can do with these? Is there a formula that you guys learned that we could apply to this when I'm using initial volume, initial concentration, final volume, and I need to get a final concentration? Oh, here you go. No problem. Anybody, come on, somebody, right? What are we going to do here?
Could you use the formula of molarity?
Which
Could you use the
formula?
formula of molarity?
Which formula of molarity?
Uh, the one that has moles over liter and then transform the total volume.
So we have initial volume,
Oh
initial
no, yeah.
concentration. Which one? You guys remember this? Come on, you guys remember this?
Yeah. Yeah. I just
C1
barely
V1
remember
equals
that.
C2 V2, right? We have to, yeah, exactly, Louis. This is what we use, M1 V, either M1 or C1, doesn't really matter, but that's what we're going to use. Yes, Brent, I didn't even see that there. Yes, is that this is what we're going to be using, right? So here we can actually calculate from this, we can actually calculate the final concentrations. That's all we need, the final concentrations. I have the KSP, right? So here, so let's take a look what we're doing. So let's actually make those calculations here. So we're going to get 0.05 molar times initial concentration of 20 milliliters is equal to 100 milliliters of this times our final concentration, right? So 0.05 times 20 divided by 100, and this equals our final concentration. So our final concentration here is 0.01 molar. Right. So we now have a final concentration of this. Or actually, you know what? I put that on. Let me do this. Uh, all right, so let's let's see. Now we had 0.5 molar times 80 milliliters is equal to 100 milliliters times the concentration. And let me put this is K plus, and this is going to be ClO4 minus. So zero point 0.5 times 80 divided by 100, that is equal to 0.4. All right, so now we have these concentrations here. So let's figure out, and these are not at equilibrium. So these are not at equilibrium because I am mixing these new concentrations together. So we're going to actually calculate Q here. So our Q is equal to, uh, what is the reaction here? Let's figure out the reaction. So we're going to have KLO for solid And we're going to get K plus some ClO4 minus, which means our Q is simply just equal to 0.01 times 0.4, and this is equal to 4 times 10 to the minus 3. 4 times 10 to the minus 3 is equal to Q. Well, the KSP for this is 1.05 times 10 to the minus 2. Is that what I wrote up here? Did I even? Yep, there it is. 1.05 times 10 to the minus 2, which means that here Q is less than KSP. That this reaction is going to shift to the right. And if it shifts to the right, are we going to have a precipitate?
No, because it's going
No,
to go to the
because it's
forward
going to go to
reaction.
these ions. Yep, it's going to go to this forward reaction. So this is no. So this is no precipitate. um, Now to bring in a little bit of what we learned in previous chapter. We talked about pH, calculating pH, pOH, those concentrations here, because some of these reactions do involve hydroxide. And if we have a concentration of OH, well, we can definitely calculate a pH value. We can definitely calculate a pOH value. And by doing that, we can, increase or decrease these pH levels by adding a certain amount of solid into the reaction to either raise it or lower that pH value. So let's try something here. How about we calculate the molar solubility of the hydroxide when enough calcium hydroxide has been added to make the molar solubility of magnesium 1.0 times 10 to the minus 5. So we need to calculate the molar solubility of hydroxide when enough calcium hydroxide has been added to make the molar solubility 1.0 times 10 to the minus 5. So this is going to do something that we call, this is what we call the common ion effect, right? The common ion effect happens when we're adding different compounds into a solution, right? Is that there's a common ion between them. So between magnesium hydroxide and calcium hydroxide, right, there is a common ion between them, right? So we can add other compounds to make other solids precipitate out. That is very plausible to do that, is adding different compounds to make other compounds precipitate. So, and we'll get back into the common ion effect in just a bit. We'll talk about it some more. So here, this is what if we're looking at this concentration here, so we're going to look at what we consider magnesium hydroxide, solid, and we get some magnesium 2 plus, plus we get two hydroxides that are both aqueous. Um, let me give you some KSP values here. So the KSP of magnesium hydroxide is 8.9 times 10 to the minus 12. All right. So calculate the concentration of OH and, you know what? How about and the pH? When enough calcium hydroxide has been added to make this concentration 1.0 times 10 to the minus 5. All right. So looking at this reaction, we do have this final concentration. If I have that final concentration, remember, back at the very beginning of lecture, we already looked at these kinds of problems. If I'm given the final concentration, oh, where'd it go? Right, perfect example here. If I'm given the final concentration of a compound, well, I know that the other compound, the other aqueous ion there is either twice that much, three times that much, is exactly the same from the reaction that we make. So taking a look back here, right, if I know the concentration of magnesium is 1.0 times 10 to the minus 5, I know that the concentration of hydroxide is twice that much, is 1.0 times 10 to the minus 5 times 2. So I know that it's twice that much. Um, and you know what? Let's see here. Let me try something. You know what? Let me try something real quick. Because I do have the KSP value. Um, let me make sure I'm reading this correctly. Calculate the OH when enough CO2 has been added to make that there. Let me do a quick calculation because we do have the KSP here. So we actually should be setting up like this. Our KSP is equal to this concentration here squared. Why is the book wanting me to do this when we can simply just do this? Minus 12 is equal to 0.0 times 10 to the minus 5. Then we can take 8.9 times 10 to the minus 12 divided by 1.0 times 10 to the minus 5 is equal to this. That value. Let's go 8.9 times 10 to the minus 12 divided by 1.0 times 10 to the minus 5, and we get 8.9 times 10 to the minus 1, 2, 3, 4, 5, 6, 10 to the minus 7 is equal to, so if we want hydroxide, we need to take the square root of that, and our concentration is 9.4 times 10 to the minus 4. Why did it want us to do it the other way? I have no idea why it wanted me to do it the other way. read the question again. Calculate the concentration of hydroxide when enough. So I don't have a final concentration because we're adding, well, yeah, I guess. So here, because we're adding additional, additional hydroxide, right? This we can consider like our spectator ion that we've done before, right? So some spectator ion, but we're introducing more hydroxide in here. So I guess I don't have the final. I guess I just can't take a look at that because not only do we have this concentration of OH, we're also adding more. I'm going to put these notes in here. We're also adding more hydroxide from here. So we actually don't have this. So we can't use that method of twice that much because we're adding additional hydroxide into there. So adding the additional hydroxide, we have to go the long way around here, calculate this concentration. But now that I have this concentration of hydroxide, we can now calculate the pH. So the pH is equal to 14 minus a negative log of 9.4 times 10 to the minus 4. And that comes out to pH is equal to 10.97. All right. So, we don't have a K. No, we're not calculating Q here. Just the pH. So this kind of is just kind of an introduction into what we consider the common ion effect. The common ion effect. We'll see more of it. I think I wanted to add some additional notes here. Oh, oh man, there's still so well. No, I don't think there's that much more to go over. We'll have to maybe catch up on Thursday a little bit. I wanted to get through this whole section. Maybe we could just do one more. We're not going to get into precipitation of halides. No, we're definitely not going to get into that. No. Okay, so let's do one more problem. One more problem. I wish I could speak more about what we're doing, but we have to learn these. There's so many calculations that we have to go over. I feel like I have to calculate. We do these sample calculations because that's all we do in gen chemistry is calculate it. Really don't have a lot of time to expand on what we're doing and why we're doing it. So let's take another problem here. So if the solution contains another problem, if a hopefully we can get it done in 5 minutes. So if a solution contains 0.0020 moles of per liter, what concentration of silver must be reached by adding silver nitrate before silver chromate precipitates. So here again, we're running into a common ion effect again, right? Is that we're adding some silver nitrate into the solution in hopes that we can get the silver chromate to precipitate, right? So if we're looking for that to precipitate, this is what we're looking to precipitate here. CrO4 solid. So we're hoping this precipitates by adding some silver nitrate into a solution of chromate. All right, so here the only thing we have, so if a solution contains 0.020 moles of that chromate per liter, that's our initial concentration. So we don't have any final concentrations here. So we are going to need an ice table. We don't have any silver just yet because we haven't added the silver nitrate. The only thing we're adding right now, so we only have a solution of this. So we only have a solution of that so far. We have some solution that contains 0.0020 moles of chromate per liter, and that's the only thing we have right now. So what we're going to be adding, this is going to be plus 2x, and this will be plus x, so this is going to be 2x, and 0.0020 plus x. Well, I think at this point we should be looking at where to get the KSP values. I haven't shown where to get the KSP. So KSP, I'm going to write it here. This is in Appendix J. So Appendix J, let's take a look at Appendix J. So here you'll see all the solubility, so the KSP here. So let's go to the KSP and find silver. And that's again in Appendix J. So here's silver, and we need silver chromate. There it is. So AgTCrO4. So the KSP value is there. It's 9.0 times 10 to the minus 12 is equal to 9.0 times 10 to the minus 12. And looking at that value, well, my K is a lot less than 1, right? It's really nice when they're a lot less than 1. The calculations are just so much easier. So if our KSP is equal to 9.0 times 10 to the minus 12, we go 9.0 times 10 to the minus 12 is equal to 2x squared times, I'm only going to use this value here because the KSP is so small. So because the KSP is so small, I'm going to put 0.0020. And here, excuse me, 9.0 times 10 to the minus 12 equals 0.4 10 to the minus 5 is equal to x. So now I have a value for x. So now we can figure out what concentration of silver do we need in order to precipitate that out. So what we have to do is, let me write this down here, that we assume that precipitation begins when the reaction quotient, the reaction quotient Q becomes equal to the solubility of the product, right? So the product, right? The solubility of the product. So when we assume that that's when precipitation begins, right? When Q is equal to this value, when Q is equal to the KSP, right, is that's when we're going to assume precipitation begins. So if we want to know, let's see, so here we're going to go 2 times 3.4 times 10 to the minus 5 is equal to the concentration of silver, where our Q will equal the KSP, and that's when precipitation begins. So that's going to be just simply 6.8 times 10 to the minus 5. So this is equal to 6.8 times 10 to the minus 5. You don't need a calculator for that. There we go. Sorry about that. Mic cut off right there. So 6.8 times 10 to the minus 5. And that's the concentration of silver we need. So if we had this concentration here, so if we had this concentration of chromate, we would need a concentration of silver in order to be, that's at least that, could be higher, but we need a concentration of silver of at least this in order to precipitate out this solid, right? In order to precipitate that out. Precipitation of halides, more common ion effect. We'll have to get to that on Thursday and then continue with the rest of the chapter. So I think let me just go ahead and stop